I certainly think it's an interesting topic. It's sort of been a strange ride from a few years ago, where a lot of years ago when I started at Tradeshift, to a place where I used the ideas that Akka happens to implement, but also the scalability questions and other things, seeing them around me, and seeing Tradeshift growing into problems around me as well, in the same way that I was discovering how these things could be addressed. And I try to, in this presentation, give you a little bit of the sort of roller coaster ride I went through while discovering this, but also with some direct hands-on advice on how you can use Akka and the related technologies to create something that scales at least to the scale that we currently need it. And for that, I'll first go through a little bit of concrete history and the challenges we've seen as Tradeshift, being a startup that went from 10 developers 5 years ago to 150 now, and a similar growth in sort of hundreds of thousands of users we currently have across the globe. And the architecture in which Akka and event sourcing play a central role that we try to roll out for much of our new development, because we feel that it gives us it takes a lot of the right features that make us feel secure in going in that direction. So when I started at Tradeshift, the application landscape was simple enough. There was a front end written in Grails, connecting to a standard Java Swingish backend, and the backend had its database that it talked to. And what could you possibly need more than that? Because you had got the front end guys doing the front end stuff, and you built your business logic. And we had this great idea of multi-tenancy, where sort of each company had their own little part of the database. And of course, if we needed more than one database, we could just create a new one, because everybody had their own database. Except for the fact we didn't actually do that. We just stuck with the one. So fast forward 6 years to where we are now. And I was actually drawing this picture and trying to sort of give you a nice overview of all the fancy stuff Tradeshift was doing. But I was drawing all these arrows with the dependencies, and I even got 1/3 of the way through. And when I stopped and realized this, it looks as confusing as it is. We have the old app backend, which is something like a plugin system we have that got revamped into the new app bank, and now we're building a new app backend, which is going to do different things yet. This is not something that we can maintain going forward, and there are scalability problems, both from the development perspective, as in now we have to hammer around in our system with 150 developers in some of the same code, where we were only 10 people before. But also, we're still around as a company, which means that we've been successful in some areas, which means we now actually have some users that try to use our systems and continuously try and bring us down by clicking buttons. And behold, that also is something that not everything was ready for when we started out. So as we found that we had more and more failures and more problems, one of the things that came out of that last year was say, okay, we kind of found out, okay, we don't want to build the two components anymore. If you have more teams, you want to build more servers. So that was somewhat obvious. But also, anything new that comes out needs to be clustered, which means there has to be at least 2 of each. And if we shoot one down, the thing should keep running as good and well as possible. Well, that's a good enough directive, and somebody might say, yeah, duh, that's how you build systems anyways. But we're still stuck with the things that we already had, and we have to migrate them somehow into something that survives all the outages. And for that, we have to take a little bit of a closer look at what's the real reason that problems occur in systems, and we'll get into that in a minute. I also want to look at the manpower growth paradigm as well, where in 2011 we were very much sort of a Java shop. We hired Java developers that knew their trade, because that's what most of our stuff was written in. Grails is pretty much Java as well. But that's not really true today anymore, because of course we started getting along with Groovy and Grails. But then as our infrastructure inevitably became more and more complex, there's tooling around that tends to use languages that are not so much Java. Turns out there's these crazy JavaScript people that even want to use JavaScript on the server. We have those as well, and then inevitably Scala creeps in, because you sort of use libraries that are written in it, and some other tooling as well. which means that we have a whole bunch of technologies now, which is not necessarily a bad thing, because the whole reason for this variety is that languages sort of solve a particular area of problems quite well. And rather than saying, everybody should use the same language, the same framework, it makes a lot more sense to allow people to use the tools that they know and the tools that they feel comfortable in, and allow them to build the systems as long as some constraints are met. And we're also trying to learn how to apply that. But going back to our technology thing, this is a typical way that a request makes it through our application, which actually I did not invent. So a request comes in from the web browser through some public API, goes to the backend, that then talks to the front end to render a PDF that talks back to the backend to get some extra information, that shoves it off to the app backend where a plugin is running, and that then kills the database because of some bug. And inevitably that goes wrong here and here and here and here, and there are threads waiting on each other, and there's more threads waiting on each other here, and then the user, after 1.7 seconds, as we know, thinks this isn't working, I'll try it again. And it just makes it worse and worse. There's a lot of connectivity between these systems that makes them, you might say, okay, we have these separate systems and our teams can work separately, but they act like one. Except for the fact that they have different code bases and different release cycles. If one of them goes down, the whole thing is down. And that's very much a problem. A problem that has, of course, been known for some while in academic and analysis circles, maybe not so much for developers that have been trying to put out Spring applications for the last 10, 15 years. But, who of you have heard of Joanne's problem, or the term let it crash? It's one of the mantras behind Erlang, the language that was started at Ericsson that actually powered a lot of their base stations, and the paradigms behind them allowed them to get 99.6 or 7 nines of uptime in a very direct sense. And that's kind of old knowledge, except that it's not typically applied in the Java world that much. Microservices is also, it's still a hot topic, but apparently the term was coined quite a long time ago. It still hasn't got much semantic behind it, besides, you write these small systems that you then can easily replace with something else, but nobody dares to say what small actually means. Should it, what does that mean in lines of code, written in what language, and then printed in what font on a sheet of paper? But it does tell us something about, they should not be big services, they should be smallish. But a more recent attempt that at least I discovered at giving a bit more sense to the discussion is the guys behind self-contained systems. And what they're saying is, well, they're saying a lot of things, but the thing that stood out most to me is, say that we have this service here, which is one component, one deployment unit, and it's serving an HTTP request to its API. Now it can do whatever it wants with its own databases, but it is not allowed to make a synchronous call out to another service to get some more information while it's answering its own request. If it wants to use something from other services, that has to come in asynchronously, ahead of time or eventually, in some mechanism that makes sense for that. And what that means is that service 1 can continue to at least answer requests if stuff comes in, and it doesn't need to have a physical direct dependency on service 2. Of course, if service 2 is down for a prolonged period of time, it might lag behind, but then it should know that it's lagging behind because of some reasonable timestamp correlation or some other things, and it can start answering, look, I'm behind, you're getting old requests, but at least you can make an informed decision and allow your business requirements to actually dictate how you handle failure. And failure is the important part in this, which is that by designing your system in this way, you have to reason about failure cases. You have to decide what you do when service 2 is down. And that's an architectural difference, but also a difference in your code, because you simply can't reach out and pretend that a method call, or pretend that a remote HTTP GET is actually just a method call that will return just like any other method call. It's a very different beast. So that's what self-contained systems gives. We've actually added a few things on top of that to try and lay out our architectural rules, and that is that we added the clusterability into it, because if you can build one of these, you can also build many. But there's also the scale thing, where as you're building a system, you have to at least have a gut feeling of saying, okay, I can handle 100 users at a time, or I can handle 1,000 users at a time, or whatever your load metric is. And what we're saying is, okay, when you know that, and you need to cover for what you expect to have, at least you should have a reasonable answer as what you would do if that is multiplied by a factor of 10. Like, can I just put in 10 more servers and it should reasonably work, or is there something else I need to do? Since it also forces that internal thought process. Okay, how do I bring this forward? What do I do when inevitably my system is successful? Since again, I'm working for a startup, but very much in other systems, if you're building out a global service, either your performance will inevitably become a bottleneck if you're successful, or you're not successful and it didn't really matter anyways. So you will hit these limits at some point, and it makes a lot of sense to be aware of that from the start. So event sourcing is one approach that happens to solve a lot of these challenges in a fairly elegant way. There are of course other means to fix it, but this is the central approach that we're taking. Who of you have heard of event sourcing before? I got a few, but let me go through it quickly. So what event sourcing does is it splits up your information domain into aggregates, where an aggregate is a unit of information on which you can make atomic claims. So either it looks like this or it looks like that, and it's never in between. It's a little bit related to your old transaction in a database. But most importantly, you don't get any guarantees between aggregates, and you could only get these guarantees within one aggregate. In this particular example, it's like a pet shop application where users can register the pets that they have, so they can buy food for them and things like that. The time is roughly going vertically in this picture. We have user 1, which at this point was created, and the name was changed to Bob. We have user 2 over here, which was created, the name was changed to Alice, and then first Alice decided to buy goldfish, and a little later Bob decided to buy a cat, and then suddenly Alice's goldfish had disappeared. And that's the timeline here. Note that the events are always in the past tense, because they are facts. They are things that have happened and will always have happened. And the way you look at these events really is as like a journal of things where you write, okay, I did this and this and this and this, and you don't come back to change that. These are facts of life. Like no matter how you change your system later on, you might delete the ability to handle pets. Bob still had a cat. And that has happened, so it makes a lot of sense to retain that. And that immutability and that append-only behavior is actually an important part of the integration that we'll get into later.
So in your example, what's an aggregate? Would that be user 2?
I'm sorry?
So in your example here, what's an aggregate? Would that be
the aggregate is the user.
Yeah.
So user 1 is an aggregate, and user 2 is an aggregate. And you'll see that these events sort of appear vertically on the slide, so they have some sort of time in them. But that's not a guaranteed ordering. Can either of you tell me why time cannot be used as a guaranteed ordering? Well, if you have your clustered application, it might mean that user 1 is running over here and user 2 is running over here. And we try our best to keep server clocks aligned, but they're usually not. I mean, even on Amazon, they can drift seconds or even more apart, which means requests might be handled in a particular sequence in reality. The server time might actually show that differently. So things might be affected before one another in reality, but the timestamps that you get are not. That's also why you can do a lot of interesting things with these events, but you have to take the time with a grain of salt. And the only guarantee you get is that within user 2, the name was changed before the pet was added, before the pet was removed. That part you know for sure, and the rest is guesswork, hand waving, and eventual consistency. And that's not as much as a problem as you might think, because very often you can make reasonable decisions with the combination of ordering and time that you get. Now, event sourcing has also been around for a while. I didn't look up when that first came to be, but the pattern is has been used in all kinds of auditing systems for quite a while, where you start out with your application that changes everything in place, and then suddenly comes the requirement, oh, I'd like to know actually what the value was before this change came in, because we have users asking for that. Can't you print a little log statement whenever that is whatever that's happening? Yeah, okay, we put the log statement in, and then comes the request, we'd actually like to analyze those things. Can't you write something that reads them out, and then come the shadow tables and other things? And turns out that made a lot more sense to write it as event sourcing to begin with. But that's still within one system, right? Your API still looks like save pet, get pet, remove pet, etc. The events in such a case, they're internal, and there might be an API to get like the audit log for some aggregation purposes, but it's typically not the main way you interact with the system. And that's actually something we're looking to change. The way that we're setting this up is that the main way that systems talk to each other is through these event streams, not through the sort of the synchronous APIs on top. They are there for user interface in some edge cases, but if you want to know something from system B, because you can't call it directly, you might as well use the event stream and respond to that. Of course, there are a lot of things you have to take into account by doing that, but that can all be solved. So let's jump into some actual code, starting with the description of the main unit of development in Akka, which is an actor. Who of you have heard of actors before? All right, a few. I'll quickly go over the definition. In Akka, an actor is like a normal Java object, except for the fact that you can't call methods on it. You can only send messages to it. And that's not an abstract thing. Sending a message to it is you get a Java object that's a message. You tell Akka, please send this message to that actor. And when it arrives at the actor can do something as a result of that message, which is either perform some side effects or send a message along to some other actors. And that abstraction is very powerful because it allows Akka to abstract the actual object instance away from the caller that does something to it. And also by making that a send operation only, and make it an asynchronous send operation, you make it very visible to the client that this is not a method call, it's not something that comes back. When you tell Akka to send a message, that is always a void operation. That you don't get a return value out of that. If you want to reply back, you need to be an actor yourself and prepare to handle messages, which is a very common pattern, but it's still asynchronous because that message might come back later, it might not come back at all, you might get several messages back, and that all depends on how you build these actors. But what it gives you is the ability to isolate problems and behavior within that actor, because if the actor, say, throws an exception while handling that message, that could mean that there was something at fault with the message itself, and you should just continue to handle the next message. But it could also mean there was a bug inside the actor, and now its private state might be corrupted. Maybe it had some fields where it was caching stuff, and when an exception occurs, you don't know whether it had changed some fields or not. Which means by default, Akka will actually take the reasonable thing and remove that actor instance completely, and create a new instance that will take over for it. But the other clients won't see that. The message that you send will no longer get consumed, but it will continue with other messages. So in many cases, it's actually a very reasonable operation where you isolate the failures to one particular object instance, and other clients don't even notice that something went wrong. Are there any questions about that? This is just a little example of how you write an actor in Java in sort of pre-Java 8 terms. This example is a ping-pong example where messages go back and forth between a ping actor and a pong actor a few times, and then the system stops. So this is our pong actor. You extend a base class from Akka, and you have to implement one method, which is onReceive, which does something when a particular message is received. As you can see, a message is untyped. There is no set type safety of messages between actors in Akka. Everything is object, so you have to make sure that you're handling a message of the right type yourself. It also means you can always extend your protocol to be something else. Typically, you'll write a class or some abstraction over this if you want more type safety. But in this case, if it was a string, we'll print something to the console, and we actually send something back to the sender. And with this code, you can see that actually there's an implicit notion of who sent a particular message. And that's very useful because anytime there's a communication between two actors, you have a back channel to communicate with. So for a typical request-reply pattern, that's extremely useful. In this case, we just tell a pong message back, which is also a string. Here's the other end of it, the ping actor, which I wrote in Java 8 style, which allows you to make things a little more type safe by using lambdas in a builder pattern that allows you to say, okay, if it was something that was this type, do this, and if it was something of this type, do that. Since that's typically how you write your actors, you have different Java classes of messages that represent different things you'd like the actor to do, and it's extremely common pattern to say, okay, if I receive something that's an instance of initialize, I want to cast that to initialize and actually do something with it. And typically, if I get a string, I want to do something with a string. And with this DSL, you already tell Java that this message is an instance of initialize, and if it wasn't, it wouldn't go in here. And if this message was an instance of string, it would execute this block, and otherwise it would go through to the next part underneath it. For this particular actor, if we send an initialize message, it will start to send some messages to the pong actor. And if it receives any string, it will increment its internal counter, and after 3 messages, it will stop itself. This actor creates a child actor, and that means that it gets to supervise that actor. So in Akka, all the actors aren't, they live in a hierarchy where you have parent actors creating childs, creating new childs, etc. And that's how you distribute your work, and you split up responsibilities as well. In this particular case, the ping actor creates the pong actor. So the pong actor knows that it has a parent somewhere that it can communicate with. But more importantly, if something happens to the pong actor, it's actually the responsibility of the ping actor to do something about that. So remember that exception we talked about earlier. If something happens to go wrong with the pong actor, it's not up to the pong actor to recover from that. The default behavior of Akka is to restart it, but the ping actor can actually influence that, and you, as a parent actor, you get to decide what actually happens to your child actors. There's a main class in which we can actually create an actor system and start the whole lot up, and what we'll see is that they start communicating and send the ping pong back to each other. Does it make sense to you that this is what would in fact happen? All right. So let's continue a little bit then, because just plain actors they're nice. They might have read about them before, what they offer, but they're not so useful in the grand scheme of things because they only live in memory. They once they go away, they die, and you still need a way to store what you're doing. Actor persistence helps with that because it allows your name kind of gives it away. It allows your actor to be persistent, but not just persistent in the sense that it replays messages. It's persistent by implementing event sourcing, and there's because of that, there's a difference between the messages that you send to the actor, which are now termed commands because that's how event sourcing, that's the event sourcing terminology, but they're still the messages that go into your actor. And what's persisted are events, and it's up to the actor itself to decide what those events are. It might be the commands themselves, but typically it's a little different. If we go back to our event sourcing example, these are events that actually happen, but if you imagine that there were actors representing these 2 users, if you had messages that you send to this actor, you could say here, create user or something. You could send that to the user actor to create itself. You could say add pet to add a pet. You could say remove pet. And that's typically the kind of language that you see in the commands that you send to an actor. Commands are typically in the imperative form where you say, do this, try and get this, get the user details, save an updated address, etc. But the events are in the past tense. When the actor agrees with what you're trying to do, it might emit some events, but it might also disagree and blow up or crash or send a message back that it's unhappy with your request. And in this example, this is a persistent actor that you could use in a chat application. So it holds a list of messages that have been exchanged in a particular channel or a particular chat room, which is just an instance variable, an array list of string. Let's go here first. When you send it a message, the abstract persistent actor base class will invoke receive command, and there's a special command to get the current list of messages. But say otherwise, if it's just a string, we call a built-in function called persist, and that's the function that will emit an event. That will say, hey, something happened. I want to put something in the event journal. In this case, it's just the string itself. So everything else in Akka persisting events is also asynchronous and will only eventually complete. So when that is complete, we add that thing to the internal list of messages that we know about. Let's go here first. When you send it a message, the abstract persistent actor base class will invoke receive command, and there's a special command to get the current list of messages. But say otherwise, if it's just a string, we call a built-in function called persist, and that's the function that will emit an event. That will say, hey, something happened. I want to put something in the event journal. In this case, it's just the string itself. So the everything else in Akka persisting events is also asynchronous and will only eventually complete. So when that is complete, we add that thing to the internal list of messages that we know about. Because like everything else in Akka, persisting events is also asynchronous and will only eventually complete. So when that is complete, we add that thing to the internal list of messages that we know about. Well, that's great. Now we've emitted events when we get a string message, but if I now kill this system and I boot it back up, this thing will still start out empty. So that's where receive recover will come in. This is going to be called whenever the actor is recovering, which means it has been freshly started, and we found some events in the journal. So while the journal is replaying, you'll get an invocation of receive recover, which with each of the events. So these are all objects that have previously been passed to persist, and you'll get them in order in the way that you earlierly persisted them. And this will all happen before the actor will start processing messages. So that way you can reconstruct your internal state as a result of events. Any questions about that? So what you should take away from this is that it's not the internal state that's persisted directly, because that actually builds up the whole array list, so you wouldn't save that. And it's not the commands that come in that are persisted either, because there's the command that just says, give me the list of messages. Maybe there's a command that says search for a particular keyword in the messages, and those are not things that they don't actually affect the state. You just search within what you already know. Another part that we kind of have to keep adding to the picture is the clustering abilities of Akka, because again, now we have our actors that can be persisted, but they're still only in one JVM. If you happen to persist them to a data store that you can reach from multiple servers, you can of course boot up a second Java virtual machine and listen on the same thing. And you have a bit of a problem, because then Akka will happily instantiate two chat actors with the same persistence ID on different JVMs, and they'll start affecting each other's state. That's not what you want. So when you want to do event sourcing with Akka persistence on multiple JVMs, they have to be able to talk to each other and agree, okay, you're going to handle this user and I'll handle these users over here, and preferably do something when something goes down, so that the users still keep working. And that's what Akka clustering does. Basically, what clustering adds to the mix is that, remember how we talked that you don't get direct access to an object when you're talking to an actor? Well, that's even more true in the clustering sense, because the object that you're talking to might not even be on the same machine. When you add clustering to Akka, the ways that you interact with actors suddenly become network aware, and you don't have to change anything in your code for that. The way you talk to an actor is still the same, but now you don't know whether the actor is actually on the same machine. It might be across the network on a different machine. And that's a very powerful mechanism that is behind the next thing we'll add to this, which is cluster sharding. Cluster sharding will use the Akka cluster of machines that are now linked together to build a pool of actors that serve a certain purpose. It's typically combined with Akka persistence, where you say, okay, I have these persistent actors, each with their own ID, and I want them to form a pool of actors that is automatically sharded across the cluster. And sharded means that rather than take a decision for each and every actor where it goes, these decisions are made in groups, in shards, so that there's less work and less overhead to keep, because you typically have like millions of users and you don't want to make that decision or remember that for each user individually. So cluster sharding is a layer between your client and the whole cluster, where it serves as a proxy, and you say, okay, I'd like to talk to user number 1, and the cluster sharding goes, okay, that's running on this node today, and it will route the request there and automatically route the responses back. So that way you can serve up the same API to all of your users on all of the nodes, and it will internally route to the correct target, and hopefully also distribute the load in such a way that it makes sense. It can't do that completely automatically. You have to write a little bit of code. Specifically, you have to write a class called message extractor that proxy will use to get messages to the right target. You have to start by specifying, okay, what's the target entity ID for a particular command, for a particular message that I'm trying to send. It's typically going to be your Akka persistence ID. So say that you have a command for our users, add pet. It would at least have a user ID where you want to send it, and maybe the pet's name. And you would put the user ID in here. So in this case, we imagine we have a chat message which has the UUID of a conversation that we're trying to send it to, and then the message itself. So this would just be the conversation. And that can be any string. Akka doesn't care how that's made up, because it will only use the hash code internally. Then similarly, it has to know what's the actual shard that should go to. And that requires a bit more ahead thinking, because it has to keep stuff in memory for every shard that exists. So your shard ID typically shouldn't be the entity ID, because that means you have to remember for every user what shard it's, on what node it's living. What works best is that you divide up your entities into sort of a number of shards that is sort of a few orders of magnitude above the largest number of servers that you expect to be running. Since a shard has to run on one node, which means if I pick 256 shards, that means with this structure, I can never deploy my application onto more than 256 nodes, because that's the finest granularity that I can get. On the other hand, I only need to keep 256 entries in memory to decide where I route my messages. And it all depends on what you're trying to route, how big you make that, but it's a balance between memory usage on the one hand and flexibility to grow without needing to do anything on the other. And then finally, you have to, if you want to, you can provide something that unwraps the message in case you have sort of a wrapper that only serves for the proxy. But that's not as important. Do you guys understand how this works? All right. Now, if you actually want to use this thing, you sort of boot up the proxy, which is the sort of the entry point towards all your cluster of persistent actors, and you have one of these on each JVM, and there is a particular way that you can get to the one singleton actor that will proxy all your requests. You have to give it a few parameters, but most of these are stuff that you don't need to customize. The only thing you have to write yourself is this message extractor that we already talked about. And after that, you, instead of talking to a persistent actor directly, just talk to the proxy, and the actor receiving the message can just use sender, and it will get whomever it was that was actually talking here. So the whole transparency thing still works. Your actor and your client don't see that this proxy was in between. And that's immensely powerful, because now you can, for example, build a REST API or something else on top of this, and it will use all the clustering features transparently. Now we knew about all of this for a while, and been following what's going on, and using some hobby time and other investments to find out what is going on. But we kind of knew, okay, this would make a lot of sense for us, because Tradeshift is a we didn't say anything about Tradeshift. They're not going to like that. But we're an online invoicing platform, or document exchange platform, which is very much transactional and is a lot about history and what did I do and who did what when, and there's a workflow involved, like who's looking at this document and doing the OK, and there's a lot of history and time-based data that we handle, and yet we're not really using this pattern as much. So we kind of knew, okay, this makes a lot of sense for us. So what we said is, okay, we'd like to do this, big, and say use our normal document handling and rewrite it in this, because there were a lot of problems with that. But it was a little risky, so we said, okay, let's try it on something new first. And we were introducing real-time chat to our system anyways, which is called collaboration in our terms. And we said, okay, well, that's also something that has very much history and other stuff in it. So let's try and do that. And that's actually running in production now. And well, it worked out really well. I mean, real-time chat and chat channels, of course, is also a sort of a textbook case for event sourcing, where you have an obvious history of what happened. You have obvious aggregates, which is the channel that you're looking at, and it's obviously has to do something with events, because you want in your web browser to show in real time as people are typing things and stuff is appearing. So that worked really well. And we are now, because that worked out so well, we are actually reworking our core document storage in our transactional layers. Also reworking our FTP upload on that. However, while doing that, we actually wrote a bit of a thin layer on top of Akka that takes some of the more generic defaults and like you can do what you want approach that's in Akka, and makes some more specific decisions that says, okay, we think in 90% of the cases this is probably going to be enough for you, and sort of a nice way to start writing an application with. And that's working out really well as well, because it means we can just show people, hey, this is one way to build an app, and we think it's probably going to work for you. Some of the default choices we made are like adding more type safety to the actor exchange, where you don't need to have throw objects around that represent your command, object that represents your event, object that represents your state, and we added a bit of type safety there. but also picking Google Protobuf as the default definition for events, for example, is something that we did, which makes a lot of sense since Protobuf is from the ground up designed to be a data format that's both compact, so it works very well in persistent storage, but it's also versioned very easily. As you go forward and you find out, oh, this event from now on also has this other field. In Protobuf, there are semantics that make the default choices a lot more easier to reason about than if you were to use JSON or XML or some of the sort of more used transient formats. And some other cool goodies in there as well that I might not have time to get into right now. But I want to show you a little bit on what the persistent actor looks like in our framework. So the first thing we do is we actually create a type that represents our command, and we say, okay, all the messages that we send to our actor have to be subclasses of that type. And now for our chat example, we have the abstract class conversation command, and we have two concrete messages that we can send to it. We can either create a new message to write some text, or we can get the current list of messages back. So those are two things we can send to the actor, and in one case it's going to emit an event. In the second case it's supposed to answer us with the current list of messages. Now events that are emitted to the journal also have their own type, conversation event. It's a boring application when we have one actual type of event, which is message was posted with an actual string in it. Would of course be more in a real system. Now what we can do is base our actor on a base class where we say, okay, we have this command type and the event type and a third type that I haven't talked about yet, which is the state that we keep in memory for this actor. And that's also split off because now our actor has no fields anymore. And an actor with no fields is a very nice actor to have because it means that you're not maintaining any state in Java. The reason that that's important is that we haven't really talked about that yet, but you want to unit test all of this stuff. You want to write tests that, you know, the business logic that you're writing, etc., works. But I just said that if you create an actor in Akka, you can't actually interact with it directly. You can't invoke methods, let alone look at fields or write a test against it. The only way you can test it is to set messages to it and expect messages back. And you should do that, and that's how you typically write tests, but it's still a lot more black box than just interacting with a plain Java class. So the more business logic that you can push outside of your actor into some other classes that you can test and write separately, the easier your testing becomes and the less you have to actually test on the actor level itself. And that's what we've done here, where you only tell it what the state class is, which is that there is one instance of conversation state, and that's the whole state of this actor. And I'll show that to you in a minute. But that state can transition from one state to the other by the events that are emitted. Actually, I'll fast forward to that first. Maybe I should have presented it first. So in this case, the state as, again, our messages. But you might see that it's no longer a list. This is Seek is a class that comes from a Java collection library that implements immutable collections. So a sequence of messages is something that it has no API to change it. And that's a nice guarantee to have because if you have an immutable object, you know that it's going to stay the same way when you look at it again. And that's a very nice thing to have in a concurrent system because then you can exchange it as a message to other things. Now, you might not typically do this with your conversation state, but the same is true for all the commands and events that we're emitting. The only method you need to write on your state class is an apply method where you put an event in and the same state should come out again, updated with whatever it is that that event did to your state. And now everything that changed in our actor is now a normal Java class again. So I can write normal unit tests against this. There's not even any Akka specific code in here. It's just something that's handling conversation events by updating itself and emitting a new conversation state. And it doesn't become an actor until I put it back into this particular class. Now for your actual actor class, besides a bit of boilerplate, unfortunately, because of the way Java deals with types, you only have to say two things. One is what state does it start out with, which is typically a static final on your state class, and how do I actually respond to events? And then there's a little structure called a handler that you can implement, where there's some certain default behavior that you would always get at least that we found, that you will always get as you're handling a command. And it goes a little bit like, okay, I want to process this command. Is it actually valid? You know, do I want to respond to this at all? Yes, no. And if it blows up, then send some error back. And if it is valid, then let's find out what the new state might become and what events I'm gonna persist. And then once the events are persisted, I probably want to update my internal state. And you know, you don't want to write all of that every time you use Akka persistence. So this handler structure, and I kind of forgot. Yeah. So here's an example of it. But you typically, the only thing that you implement is, okay, if I get a command of this type, in this case, the post message command, what events am I actually going to emit? Which again is an immutable sequence of conversation events. It could be nothing, it's also fine, but it could be one or more events. And what reply should I send back to the sender as part of my protocol? Now, in case of post message, I don't have actually anything to send back because somebody's told me, please post a message. But they might want to know when I'm sure that I've actually persisted this message. So there's a token or something I want to send back. And in this case, there is an Akka class called done, which only has one singleton instance, which means, okay, I'm done with whatever I'm doing. But there could be any old object that you send back that goes back to the client implementing that. So we are trading a little bit. We now have a way to cluster our application across multiple JVMs, a lot of them, even if we want to. And we are creating this event journal, but as far as our code goes, we still only have access to that event journal from the individual aggregates. So how do we get the nice asynchronous replication and stuff built up? And there we use another part of Akka, which is the ability to query the event journal in arbitrary ways. They have a little bit of a fine-grained API that they define, but it depends very much on the implementation, what you actually get. But one thing that most implementations implement is the ability to say, give me. Very much depends on how am I storing them. You know, is it Cassandra? Is it LevelDB? Is it some other data store? And what kind of guarantees does it give? How long am I willing to wait for all the servers to have written it? And there are millions of knobs you can twist to make it more real time or more correct. But the good thing about that is that the knobs are there, and you know in your face that it will only go from real time to more correct. You can't get to fully correct because you know the edge cases do happen. But what we did is we took that query API that gives you this continuous flow of events, and we simply bound that to HTTP in the simplest way we could think of. That doesn't involve WebSockets yet because that's you know, it's also old. It's not as pervasive as plain HTTP. So we chose to, and we only need one way, right? Because the events only go out the TCP stream. You don't need to send anything back. So we do an HTTP chunked encoding where one HTTP chunk is one event, and that's a simple mental model to use, at least if you know HTTP or you read up on what it is. Chunked encoding has been around for a while, so most clients support that, and that's really nice because now you can send a normal HTTP event, get/event. You can even jump into the middle of the stream by roughly milliseconds again, and out come the chunks of stuff that has happened since that period. But because it's a normal TCP, we know, and then as new events come in, as users are using our system, we just reuse that same TCP stream and keep sending events out. So we now have an API that unifies the ability to query historic data with the ability to react to stuff in real time. And that's now suddenly the same thing. Where if I'm building a new application, say I want to summarize what keywords are hot in our chat application. I wrote my code, I used this API, and by simply calling into get events since equals 0, I can, of course, roll out all the events into my nice, you know, inverted search index of whatever technology I'm using. But when I'm done, I'm not actually done. This stream will simply block, and my client will block, and as soon as there's a new event, I'll automatically process that as well, because it's what I was doing beforehand as well. And that's turned out to be extremely powerful and very nice for clients to use, because you don't need to pull and say, okay, is there new stuff? Is there new stuff yet? Since what? Where was I? Etc. You do need to remember where you were, but only if you reboot. In normal operation, you have this stream open continuously, and as the events come in, you'll do with them as it makes sense. And that's actually how the collaboration stuff worked. So when we built that, there was the backend with Java and Akka and all the nice clustering stuff we talked about. and it was a completely different team of people with different skill sets, sort of the front-end team. I chose Node.js and a normal Postgres database to save some metadata and some other stuff about these conversations. And we only communicated through that event API and the protobuf definitions underneath. And that worked out really nicely because they could really build their application how they wanted and specific to the views and things that they wanted to remember, while we could still have full control of what happens and what other guarantees we get on the Java side. And in the end, of course, they do have WebSockets to the web browser because that's what makes most sense in the modern world. And the second thing that we realized is that we started off building only the new things, but it turns out we had an old workflow system that talked about a little bit where, okay, you assign a document to somebody and somebody else comes along, and that uses a database that, if you look at it the right way, kind of looks and smells like an event journal. So even though they didn't really use Akka or any of those technologies, we could just view that database as an event journal as well, and use the same kind of techniques to actually now intermix the chat messages with some semantic changes that happen to documents and provide it in a unified way to the user. And that's not something we deliberately did up front. This is something that comes as a result of this asynchronous architecture where at any point you can decide, ooh, the way that I stored this data here in Postgres,
Hello.
that's all right. So the where was I? So you can yeah, right. So you figure out the schema that we picked for the Postgres database isn't quite what we wanted. We want to have these workflow. The columns that I picked aren't really the right ones. Since all of this is asynchronously replicated, what I can do is I can write version 2 of the application with its own Postgres server and its own servers, and just hook that up into the event stream while version 1 is still running. And once that's done materializing in a different way into Postgres, I can do a swap over directly. The users wouldn't know that anything has changed, but I've completely changed technologies if I wanted to. And that's an extremely powerful aspect of this as well, that as long as any changes that happen outside of this journal are is it? Ah, there we go. So, and we've done that a few times. So, the Node.js guys, being the hipsters that they are, they actually started out with MongoDB until somebody told them that I might want to take something a bit more proven first, and these kind of iterations have been made, and that worked out pretty much how we wanted to. So we kind of know that both the development part of it and the technology part of it is going in the direction that we want. But there are still challenges. The one thing is that we've they're finding out what's going on, and they we've gotten more and more involved with Akka and development around Akka as well, and a lot of these technologies are still being fleshed out. Like the Cassandra plugin has TypeSafe has started to maintain that themselves only half a year or so ago, and since then quality has really gone up, and we certainly think that it's production ready, because in the end an event journal is a fairly simple thing, right? I mean, you store stuff that's ordered only by one key, and you can kind of, if you've seen a little bit of Cassandra and HBase and Amazon's equivalent, and you kind of know where that's going. But still, you need to think about what these things are doing, and it is a fairly young combination. My second thing is that even though our systems fail all over the shop,
there's still this built-in attitude that, okay, building systems, I know that, I know Spring, I know Java, I know my threads and if I want to do communication, I just do synchronized over here, and then we can do it that way, and then we have these fancy parallel collections, and then use those if I want speed, and getting that mindset moved to sort of that plane of that independence between components and asynchronicity is taking a bit of education and massaging and inviting people to think in a different way. Now, the good news is that if you actually want to get involved with this and think, okay, so how can we actually build systems like this? There's a workshop tomorrow in I think this room where we'll go a lot more in depth, and there will be no slides and mostly code on actually getting something built with Akka and in a clustered way. So if you're at all interested, then please drop by. Any final questions? Yes, please bring your laptops. Yeah, otherwise you can look at my laptop. That's, yeah, thanks a lot.